So we've spent a good amount of time learning how to write chemical equations for the different types of reactions, especially the 5 main types of reactions. We're going to take a look at a different way of writing these equations now called net ionic equations. And as you can see here, it's just the important stuff in a chemical reaction. So to start with, by way of contrast, what we've been writing are called full molecular equations. And full molecular equation shows complete formulas for all species involved in the reaction. The word species in chemistry means an ion or molecule or element involved in a chemical reaction. So it's a catch-all term for the particles. By contrast, a net ionic equation only shows the species that are actually changing in the reaction. Remember, a chemical change involves a change from one substance into another. There are parts of some reactions that don't actually change, and therefore if they're not actually changing, they're not really participating in the reaction. And in a net ionic equation, we don't include those. This will make a little more sense as we do some examples. To start with, we have to understand something about solubility. Okay? When ionic compounds dissolve, they split into the corresponding ions that make them up. Okay? That's the first thing we want to understand. The ions themselves are surrounded by water molecules and they're separated from one another. So they can't stick together anymore because the water molecules are sort of surrounding them and separating them. And if they can't stick together, they can't form solid crystals, precipitates. So the compound seems to disappear because the particles, these ions surrounded by water molecules, are too small for you to see them. So it looks like they're just gone. But in fact, they're just separated into very, very tiny little particles. Okay? This is a little schematic of what's actually happening here. Remember, water is a molecule that is polar. That means that it has a negative end where the oxygen is, and it has a positive end where the hydrogens are. And these little red and white molecule models are water molecules. The red is the orange and the white are the hydrogens. The red is the oxygen and the white are the hydrogens. So the red end, the oxygen end, is the negatively charged end. And that end can surround a positively charged ion and insulate it, keep it away from its negatively charged partners. And similarly, the water molecules can point their positive ends at a negative ion and surround it and keep it separated. So essentially, when you have something dissolving, that's what's going on. The water is coming in and it's pulling these ions off of the main crystal and surrounding them, pointing the appropriate end of the water molecules inwards towards the ion. Those ions can't get close to each other, they can't stick together, they can't form a crystal. Okay? So net ionic equations will show anything that is ionized, anything that is soluble, aqueous, as a mixture of the ions instead of as a neutral formula. And that's going to be really the key to it. Okay? Precipitates, anything that's a solid, or molecular compounds, they don't ionize, they don't form ions. So we don't change their formula, we leave the formula alone. So really this is the basis of how we're going to do our net ionic equations. Anytime something is aqueous, we're going to split it into its ions. Anytime it's a solid, precipitate, or a molecular compound, a liquid or gas, we leave it alone. Okay? If there are ions when we do this, if we look on both sides of the equation, we see ions that don't change from one side to the other, they're exactly the same, then they're not really doing anything. And we call those spectator ions. Spectator ions we don't include in the reaction because they're not actually reacting. They're just there to bring ions into the game, so to speak. Okay, so let's do an example. We'll start with the basics. Let's write a full molecular equation for this, okay? I want to write a balanced chemical equation for the reaction of barium chloride solution with sodium sulfate, okay? These are both going to be aqueous solutions. So some things to consider is we need to know which type of reaction it's going to be. We need to predict the products based on the type of reaction. And we need to remember our solubility rules so we can figure out if there's any precipitates on the product side of the ring. So barium chloride is BaCl2, aqueous. And sodium sulfate is Na2SO4, aqueous. Okay. The first thing we want to know is what type of reaction is this? Well, I've got two aqueous ionic compounds. That means it's double displacement. And in a double displacement reaction, I switch the positive ions. So the barium will switch with the sodium. Barium is +2, sodium is +1, so I'm going to get BaSO4 for barium sulfate, and I'm going to get NaCl for sodium chloride. Now I need to balance this because I've got 2 for sodium chloride there, so I'm going to do that, 2, and that should do it. That should take care of what I need. I also need some state symbols, so I need to figure out my solubility rules. Chlorides are generally soluble unless they're with silver, mercury 1, or lead 2. When they're with alkali metals, though, they're definitely soluble, so that's aqueous. Barium sulfates. Sulfates are usually soluble unless they're with barium, as one of the examples. So barium sulfate is actually a solid. It's my precipitate. Okay? So this is the full molecular equation for this reaction. All right? Now, we want to be able to write a net ionic equation, so we have to learn how to do that. There are some steps that we're going to need to follow. So to write net ionic equations, we have to do a few things. The first thing is we start with a full molecular equation. Okay, we've done that. All right, we've got to start there. The next thing we're going to do is we're going to separate all aqueous substances into ions. Okay, so anytime we see an aqueous, we're going to split it into its ions. We're then going to identify the spectator ions and get them out of there. Spectator ions, remember, are ions that don't change. And then finally, we're going to balance the net ionic equation at the end with respect to both atoms and charge. That's important. Okay? We don't need state symbols at this point because we can assume that if we see an ion by itself in a chemical reaction, it has to be in solution. There's no such thing as just ions by themselves. They are either dissolved in water or they're with another ion in a compound, a precipitate, okay, a solid compound. All right, so let's give this a shot and see if we can take our first example and write a net ionic equation for it. So the first thing we're going to do is we're going to separate anything that's aqueous. Well, that's aqueous. That's aqueous. That is not. That's a solid. I'm going to leave it alone, but that's aqueous there. I'm also going to ignore any balancing I've done at this point. It just makes it easier if you ignore the balancing. Okay? So this is aqueous, so this splits. This splits into what? Well, it splits into the barium ion, Ba+2, and the chloride ion, Cl-. Okay? Sodium sulfate splits into the sodium ion, Na+, and the sulfate ion, SO4 -2. And again, I know there are 2 sodium ions. I don't care. I just want to list the ions that are in these species. Okay? Now, the barium sulfate, we leave that alone. And the reason we leave it alone is because it's not aqueous. Therefore, it's not dissolved. And if it's not dissolved, it's stuck together. But sodium chloride is dissolved, Na+ and Cl-. So this is a full ionic equation. We've split up any of the aqueous substances into their ions. Now we've got to identify any ions that are exactly the same on both sides. Well, I see a chloride ion here and one that looks exactly like it over here. I see a sodium ion here and one that looks exactly like it over here. Notice, yes, there's a barium here and a barium here, but they don't look exactly the same. This one has a charge. This one is part of a compound. Same thing with sulfate. So I leave those. The other ions, the ones that are exactly the same, I'm going to get rid of. I'm going to omit. And so I'm just going to write what's left. Ba+2 plus SO4 -2 goes to BaSO4. Okay? That's my net ionic equation. Now I need to make sure that it's balanced with respect to atoms. 1 barium, 1 sulfur, and 4 oxygens. 1 barium, 1 sulfur, and 4 oxygens. And respect to charge on both sides. I have a +2 and a -2. That means 0. This is neutral. That's 0. This is my net ionic equation for this reaction. And that's only the important stuff. That means that in this whole reaction up here, the only real thing that happened was barium ions and sulfate ions got together to form barium sulfate. The sodium and chloride ions were not part of the reaction. All they were there for was to bring those 2 ions together. That's their entire purpose. Okay? Let's take a look at a second example. We're going to write a balanced net ionic equation for the reaction of magnesium metal in silver nitrate solution. Okay? Write this down, and then let's try to write our net ionic equation for this. You ready? So, magnesium metal, Mg, solid. Silver nitrate, AgNO3. Well, this looks a little familiar. As a matter of fact, this was one of the reactions that happened in your lab. type of reaction. A metal plus an ionic compound, that's single displacement. I need to check to see if magnesium is more reactive than silver, so I need to check the activity series. And when I do, I see that yes, magnesium is more reactive than silver, so magnesium will come in here, it'll kick the silver out, the silver will come out as just plain old silver metal, and the magnesium will go with nitrate. Mg is +2, nitrate is 1 minus, NO3 minus, so I need 2 of those. Silver is the metal, it's solid. Magnesium nitrate is a nitrate, and all nitrates are soluble, so that's aqueous. So there's my full molecular equation. Now, I haven't balanced it. I should probably do that, right? I'll put a 2 in front of the AgNO3 and a 2 in front of the Ag to make it work. Now I'm going to split anything that's aqueous. Well, magnesium is not aqueous. It's a solid, so I'm going to leave that alone, Mg. This is aqueous, AgNO3. So I'm going to split it into its ions. That's the silver ion, Ag+, and the nitrate ion, NO3-. That's that one. Silver is a solid here, Ag, leave it alone. Magnesium nitrate is aqueous, though, and that's made of the magnesium ion and the nitrate ion. Okay? Now I'm going to look for spectator ions. Remember, they must look exactly the same on both sides. Silver here has a +1 charge, and here it has no charge. That's not exactly the same. So they're not spectator ions. They're part of the reaction. That's a change. This is going from charged to neutral. Magnesium is 0 over here and +2 over here. That's a change. It's going from no charge to +2. But the nitrate is exactly the same on both sides. The nitrate hasn't actually done anything in this reaction. So I'm going to eliminate it. And what I'm left with then is Mg plus Ag plus goes to Ag plus Mg plus 2. Now I need to balance this with respect to atoms. Well, it is 1 magnesium, 1 silver, 1 silver, but not with charge. On this side, I have 0 and +2. I have a total of +2. On this side, I have 0 and +1, a total of +1. The charges have to balance. I need 2 silver ions to give me 2 positive charges, and that means I need 2 silver atoms over here. You'll notice, though, that we had those 2's in place back up here. So you can kind of cheat and look back up here, and that's probably what you're going to be needing to do. So this is my balanced net ionic equation for this reaction. All that's actually happening here, the nitrate is irrelevant. It could be any counter ion. All that's happening is that magnesium is reacting with silver ions to form silver metal and magnesium ions. And if you think about this really carefully, this is just a transfer of electrons from magnesium to silver. That's all it is. But we'll see about that later on. Okay? So it takes a little bit of practice, but if you follow the steps, it should make sense and it should be fairly easy. That's net ionic equations.